Imagine living hundreds of miles above Earth. You're surrounded by the vacuum of space, but somehow you have everything you need, not just to survive, but actually thrive up there.
It's an incredible achievement, really.
And it's all made possible by something most people don't think about much: space logistics.
Yeah, the critical, often unseen part.
So today, we're doing a deep dive into these unsung heroes, the cargo vehicles that keep the International Space Station supplied.
The lifelines, basically.
Exactly. Our mission here is to unpack the different spacecraft they use, how they work, why they're so vital for keeping the ISS going, and, what this all means for the future, where space exploration and logistics are headed.
That's right. Because if you want to understand how humans maintain a foothold beyond Earth, you absolutely have to understand how we keep things running, how we get the food, the water, the spare parts, everything up there.
You mentioned how critical it is. We all see the headlines about astronauts, the crewed missions, which are amazing, obviously. Yeah. But what makes space logistics so uniquely challenging compared to, say, running a global shipping network here on Earth?
Well, the scale of the challenge is just immense. It's vastly more complex. The stakes are incredibly high compared to any terrestrial supply chain.
You mean the cost?
The cost is astronomical, literally. Back in the space shuttle days, estimates were around $10,000 per pound just to get something into orbit.
$10,000 a pound.
Yeah. Now, SpaceX is aiming for maybe $1,000 per pound, which is a huge improvement, but still, it's exorbitant.
Wow.
So the key insight really is that space logistics isn't just a hurdle. It forces this radical rethinking of everything. Design, manufacturing, how we even think about using resources in space. Every single ounce of efficiency is absolutely critical.
So when you're dealing with costs like that, what does that force engineers and planners to do? Is it just about being efficient, or does it change what they even send?
It's both. Definitely both. It changes everything. The materials they choose, how they pack things, or rather how they don't pack things, eliminating packaging entirely. If you can shave off even a few grams, you do it. It's worth it. And this isn't exactly a new problem either.
So how far back does this thinking go? Were they worried about supply chains right from the start of the space age?
Oh, absolutely. The roots of space logistics go way back to the 50s and 60s with the very first satellites and probes. You have to figure out how to get them there and keep them functional.
Okay.
But the International Space Station, the ISS, that's really been the ultimate test case, the proof of concept for humans living in space long term.
And it was originally designed for, 15 years? The first piece went up in late 98.
That's right. So its original end of life should have been around 2013.
But here we are?
Exactly. Nearly 3 decades later, and it's still operational. And the insight from that, from the ISS's long life, it's profound. It shows long-term human presence isn't just about launching people.
It's about the supplies.
It's about mastering this art of continuous, flexible resupply. It proves that with that relentless logistical support, what we thought might be a temporary outpost can become, a permanent evolving base.
And operations are now agreed through 2030, right? And they're even looking beyond that.
Yes, agreed through 2030, and feasibility studies are looking towards 2040, maybe even further. It's quite remarkable.
So who are the workhorses? Who are the real heavy lifters doing this resupply job today?
Okay, so right now there are 4 main active cargo vehicles regularly visiting the ISS.
4 main ones.
You've got Russia's Progress vehicle, then 2 from the U.S. Cargo Dragon 2 and Cygnus, and also China's Tianzhu, which services their own station but is part of the overall picture of space logistics.
Okay, let's start with Progress, the Russian workhorse, you called it.
It really is. Progress is a true veteran. It's an expendable cargo ship, meaning it's single use.
Okay.
And it's actually derived from the Soyuz spacecraft, the one that carries cosmonauts.
So it's based on a proven design.
Very much so.
Okay.
It has 3 main parts. There's a pressurized module for cargo like food, clothes, science experiments, that kind of stuff. Then an unpressurized tanker section. This carries fuel for the station and water. And it's designed really carefully to prevent any toxic fuel fumes from getting into the station's air.
Makes sense.
And finally, there's a propulsion section at the back. That handles the automatic docking and can also be used to boost the station's orbit.
And its history goes way back, doesn't it?
Way back. Maiden flight was 1978. It supported the old Salyut stations, then Mir, and now the ISS for decades.
Wow.
And its unique feature, or maybe its defining characteristic, is that it's disposable. Once it's delivered its cargo and been unloaded.
They fill it with trash.
Exactly. They load it up with waste from the station, seal it up, undock it, and send it on a controlled trajectory to burn up safely in the Earth's atmosphere. It's like the ultimate space garbage truck.
They probably never miss collection day up there.
Probably not. And speaking of operations, there's actually breaking news today, July 3rd, 2025.
Oh, yeah.
What's happening?
Progress 92. Its designation is Progress MS-31. It just launched from Baikonur.
It's carrying about 3 tons of supplies. And just to give you a feel for the breakdown, that's like 1,205 kilograms of dry cargo food, experiments, spares, then 950 kilograms of fuel for the station, 420 kilograms of water, and even 50 kilograms of nitrogen gas to replenish the station's atmosphere.
They track it down to the kilogram.
Every single bit. It's expected to dock automatically to the Poisk module on July 5th.
And didn't one just leave?
Yes, good point. Progress 90, or MS-29, departed just a couple of days ago, July 1st. It's this constant cycle, this ballet of arrivals and departures that keeps the whole thing running.
It's amazing choreography. And sometimes they get there really fast, right? Didn't one set a speed record?
That's right. Back in 2018, Progress MS-09 made the trip from launch to docking in just 3 hours and 48 minutes.
Under 4 hours. That's incredible precision.
It really highlights how refined the process has become.
Okay, so that's Progress. Moving over to the American side, we've got SpaceX's Cargo Dragon 2. What's its standout feature compared to Progress?
The big one is reusability. Unlike Progress or the other U.S. vehicle Cygnus, Cargo Dragon 2 can come back.
Return trip capability.
Exactly. It can return a significant amount of payload, up to 2,507 kilograms, safely back to Earth, splash down in the ocean.
And that's crucial for science, right? Bringing samples back.
Absolutely vital. For scientific samples, finished experiments, broken equipment that needs analysis, it's a game changer. And it can also carry both pressurized cargo inside and unpressurized cargo in its trunk.
Gotcha. So reusable and returns payload. Then there's the other American one, Cygnus from Northrop Grumman. How does that one work?
Cygnus is more like Progress in that it's expendable. It also burns up on re-entry after its mission.
Okay, so another garbage truck, basically.
Pretty much, yeah. A key difference from Progress, though, is how it arrives. Progress docks, automatically it flies itself right into the port.
Right.
Cygnus uses a method called berthing. It flies close to the station, then the station's robotic arm, the Canadarm2.
The big arm.
That's the one. It reaches out, grabs Cygnus, and then carefully maneuvers it into position to bolt it onto a port. The enhanced Cygnus model has a pretty decent volume, too, about 27 cubic meters.
So Progress docks itself. Cygnus gets grabbed by the arm. Interesting difference. And you mentioned China's Tianzhu.
Yeah, Tianzhu is China's cargo vehicle, primarily for their Tiangong space station. It also uses automated docking, similar to Progress.
Okay, so those are the 4 active ones. But have there been others in the past? And what's coming next?
Oh, yeah, definitely. We've seen some really capable vehicles retired. The European Space Agency's ATV, the automated transfer vehicle, was a beast. It could carry up to 8.85 tons.
Wow, that's like 3 times a Progress load.
Roughly, yeah, it was huge. And Japan had the HTV, the HII transfer vehicle, another major contributor. Looking ahead, there are new players coming. Sierra Space's Dream Chaser cargo version is expected soon, and Japan is developing the HTV-X, so the fleet is always evolving.
It really is a constantly changing landscape.
Right.
And all these vehicles, past and present, they've supported this incredible structure, the ISS. It's just amazing, a marvel of international cooperation.
Yeah, absolutely.
25 years in orbit now, over 270 astronauts have visited. Given that it was only designed for 15 years, how did they manage to stretch its life so dramatically?
Well, its longevity isn't luck. It's the result of some serious engineering and, crucially, a lot of proactive work.
Right.
Extending its life beyond that initial 15 years took a massive effort across multiple disciplines.
And now it's funded through 2030, with hopes for even longer.
Right. And the why is important. Why keep it going? Well, it maintains that crucial human presence in low Earth orbit, LEO. It's a test bed for new technologies for LEO itself, but also for lunar and deep space missions.
Testing ground.
Exactly. Plus all the microgravity research that benefits us here on Earth. And really importantly, it allows for a smooth transition to whatever comes next, likely commercial space stations. We don't want a gap in LEO presence.
Makes sense. And I imagine the analysis to confirm it's safe to keep operating is incredibly complex. What kinds of things do they have to check?
Oh, everything. They're constantly monitoring structural integrity, looking for any material degradation, fatigue, corrosion, radiation damage. They assess the life support systems, the electrical power systems, the thermal control.
The plumbing, the wiring.
Pretty much. And of course, logistics and maintenance are huge parts of it. Do we have the critical spare parts? Is the supply chain robust? Are components becoming obsolete? How do we manage storage on board? It's a massive, ongoing undertaking to keep this nearly 30-year-old orbiting lab running safely and effectively.
It really is. And all that incredible engineering, all that logistical planning, it all supports the reason it's there.
Yeah.
The science. Let's talk about what's happening right now. Expedition 73 started back in April 2025. What are they working on?
It's a busy time up there. There's an international crew of 11 astronauts right now from 6 different nations.
11 people. That's crowded.
It is, and they're juggling a lot of science. Recently, they've been measuring blood flow changes in the brain in microgravity, working with brain-computer interfaces.
Wow.
Doing really high-resolution eye scans. Astronaut vision is a big concern, so they're even testing things like vitamin B supplements to see if that helps protect their eyes.
Interesting.
Also using electrical muscle stimulation to combat muscle atrophy, taking hyperspectral images of Earth. It's a very active laboratory.
And they've been doing spacewalks too, right? EVAs?
Yep. EVA 93 was completed on May 1st. That was Anne McLean and Nickel Ayers installing modification kits for the solar arrays, upgrading the power system.
Okay. And there are crew rotations happening too.
Always. The Axiom Mission 4 private astronaut crew is expected relatively soon. Preparations are underway for the next NASA crew rotation, Crew 11. And the Russians are actually shifting to longer duration missions, now some cosmonauts staying for 8 months instead of the usual 6.
8 months. Wow. Now, while it's amazing it's still going, it's not all smooth sailing, is it? There have been some issues reported.
That's true. There have been reports, particularly concerning the Russian Zvezda module, about small cracks and ongoing pressure leaks. They're being monitored very closely, of course.
Right.
And you also have the background issue of NASA budget deliberations. That always plays a role in long-term planning, especially as the ISS heads towards its planned end of life and deorbit sometime around 2030 or 2031.
So, looking beyond the ISS then, all this expertise, this logistical mastery we've developed, what does it mean for the future? It feels like we're shifting away from just relying on Earth for everything.
That shift is absolutely inevitable, and it's already happening, driven largely by innovations like reusable rockets. Companies like SpaceX, Blue Origin, they're driving down launch costs dramatically.
Which makes more missions possible.
Exactly. More frequent missions, more ambitious missions. That lower cost is the foundation for everything else.
And here's where it gets really interesting, I think. Space-based manufacturing, using resources actually found in space. That sounds like the real future of logistics.
It's the linchpin. It is the game changer. Imagine, instead of launching every single screw, every bracket, every liter of water or kilogram of fuel from Earth at enormous cost.
You make it there.
You utilize resources that are already in space. Water, ice from asteroids or the moon, minerals from asteroids, regolith on the moon or Mars. You process them in situ.
In situ resource utilization, ISRU.
That's the term. It drastically cuts the logistical burden. It's what will enable us to truly expand, to go deeper into space, build permanent bases, maybe even settlements. It's about creating a self-sufficient ecosystem off Earth.
So you need robust supply chains, even if they originate partly in space. How do you build resilience into that?
Yeah, resilience is key, especially when you're operating so far from Earth with long lead times. It means redundancy, having backup systems, multiple suppliers if possible. It means stockpiling critical components.
Like having spare parts depots in space.
Exactly. And eventually establishing those space-based manufacturing capabilities we talked about. If a part breaks on Mars, you don't want to wait 2 years for a replacement from Earth. You want to be able to print it or build it right there.
Makes sense.
And another huge part of this future is autonomy and robotics.
Robots doing the heavy lifting.
And the smart lifting, too. Think about space-based supply depots that can autonomously receive shipments, manage inventory, and fulfill orders sent from Mars or a lunar base. Think robotic workforces, assembling structures in orbit, doing construction on the moon, even mining asteroids.
So fewer humans needed for the dangerous or tedious logistics work.
Precisely. It's not just about efficiency. It's about safety, capability, scale. Moving from largely manual, risky operations today to a much more automated industrial presence in space tomorrow.
That vision of an automated space economy, it's fascinating. But as we push further out, what about the rules? How do we manage all this activity?
That's a critical question, and honestly, one we're still figuring out. We definitely need expanded regulatory frameworks. How do you manage space traffic? Who owns space resources? How do you ensure sustainable practices?
Big questions.
Huge questions. And it will require much more international collaboration than we even have now. But what's clear is that private companies are increasingly in the driver's seat.
They're the innovators pushing this forward.
They really are. They're tackling these complex logistical challenges head-on, often in partnership with government agencies like NASA or ESA, but they're providing a lot of the momentum for deep space travel and potential colonization.
Well, this has been quite the journey. We've gone from the vital, maybe sometimes overlooked cargo runs keeping the ISS alive today to the amazing engineering that's extended its life. And then looking ahead to this really exciting, challenging future for supply chains way beyond Earth.
It really connects the present necessity with future possibilities.
So here's a final thought for you to ponder. Imagine a future where these space-based resource hubs, these autonomous robotic factories, completely change how we think about supply chains. It's not just a line from Earth out anymore, but maybe a self-sustaining, almost circular economy within the solar system.
Detached from Earth-based logistics in many ways.
Exactly. When we truly make that break, what unexpected challenges, but also what incredible opportunities might pop up that we haven't even conceived of yet.